Hi, Doc Revis here with Watch Me Work It. What is the ms spin value of an element based on its electronic configuration? So watch me work it. So here's a typical problem. What is the ms spin value of the following elements? So we're just going to pick an element and work this through. Now, as we work it, you want to recall that ms spin means you have either a plus 1/2 for a electron pointing up or spin up, and you have a negative 1/2 for an electron or arrow pointing down. So those are your two choices. It's either going to be spin up plus 1/2 or spin down minus 1/2. So let's pick an element here. Let's do carbon. So if we have carbon, we can do the electronic configuration as 1s2, 2s2, 2p2, and I know that's 2 because 1s2, 2s2, 2p1, 2. Okay, that's carbon. All right, so now if we want to see what this looks like for the spins, we draw out the diagram, the electronic configuration diagram. Let's draw 3 bars for the p orbitals because we can populate with a max of 6 electrons in 3 degenerate levels there at 3 degenerate orbitals. And so if we populate this, we have 1, 2, 3, 4. Now, Hund's rule says I must distribute before I pair. So this would be 5, 6. So my last electron in is pointing up. Therefore, my spin is plus 1/2. Okay? Let's do another one here. Let's do oxygen. If I take oxygen, I have an 8. And what I'm going to do is I'm just going to start with the 2p orbital since I know the 1s and the 2s, they're already filled. And we're just going to start with the p orbitals to complete it. So this will be the 2p for oxygen. Okay. And so oxygen on the p is going to have 1, 2, 3, 4. Okay, show you again. 1, 2, 3, 4 electrons. So we have to distribute before we pair. So 1, 2, 3, 4. Therefore, the spin value here is minus 1/2. Okay. All right. Let's do neon. So we have neon. We need only to deal with the 2p orbitals to determine its spin value. Neon has a total of 10 electrons, but we can start with the p. In the p, we'd have 1, 2, 3, 4, 5, 6 in the p orbitals. So we have 3 degenerate p orbitals. So that's your 2p again. And that's going to be 1, 2, 3, 4, 5, 6. And therefore, we have again another negative 1/2 spin. It's interesting to note that what you find is that the first 3 will populate with a plus 1/2 spin, and the last 3 will populate with a minus 1/2 spin. Okay. Let's just do one more here. Let's do chromium. So if we look at chromium, and for chromium, we're just going to start right in at the d orbital. Okay, since the others are completely filled. So we start at 4, quantum number 4 in value 4 for this period. And so we are going to draw out our 5 degenerate levels for the d orbitals. D orbital has 5. Since it has 5, that means it maxes out at 10 electrons. So this is going to be our 3D. It's 3D because it's n minus 1 for 3D. And chromium is going to have here 1, 2, 3, 4 electrons. So 1, 2, we must distribute, 3, 4. So its spin is going to be a plus 1/2 here. Okay? All right? And so we can also observe that if you count over the first 5, 1, 2, 3, 4, 5, the first 5 are going to be plus 1/2 spin. and the next ones are going to be minus 1/2 spin. Okay? By the way, if you did the s orbital, it gets really crisp and clear. This is going to be a plus 1/2, and this is going to be a minus 1/2 spin. All right? Let's play another game here. How do the ms spins of the following elements compare? So based on the trend I just told you or plotting them out, we could compare some things. So let's compare boron with carbon. So if we write up the electronic configuration diagram of the p orbitals in boron, we'd have 1, 2, 3, and this would be our 2p. Likewise, with carbon, 1, 2, 3 for carbon. Okay, so we have a carbon here with the 2p, and for boron, we would have 1 electron, and for carbon, we would have 2 electrons. So how do they compare? Well, this is plus 1/2, and this is plus 1/2. So that's how these spins compare. The difference is, however, in its location, its ML location. ML, as we know, the ML is plus or minus. The L value gives direction, magnetic direction, or location. And so to label it, we always start at the center point. I'm going to just write it right here. This is 0 plus 1 minus 1. Start at the center point. Do it like a number line. 0 plus 1 minus 1. So for a boron, we have a plus 1/2 spin in the minus 1 location. For carbon, we have a plus 1/2 in the 0 location. Okay? Let's just compare a couple of others here. Okay? Let's compare manganese, and then I think we'll compare it to cobalt. Okay? So we would have the 5 degenerate D. So this is going to be, now we're here in the D, this is going to be a 3D. Okay? So 4 here, so this is 3D. So we're going to write out our 3D orbitals here. So this is I'm going to write down here a little lower, 3D here, and this is a 3D here. And we're going to populate this with electrons for the D. For manganese, we have 1, 2, 3, 4, 5. We conveniently count it on the periodic table there. And this is going to be 1, 2, 3, 4, 5 for a plus 1/2. And how does that compare to cobalt? Well, for cobalt, we're going to have 1, 2, 3, 4, 5, 6, 7. So we're going to have 7. So 1, 2, 3, 4, 5, 6, 7. Again, remember Hund's rule said we have to distribute before we pair. And so when we do this, we discover we have here a negative spin 1/2 here. Okay, all right, it's a 3D there. So we have a negative 1/2 spin. But with regard to the location, I'm going to squeeze it in, the locations in here somewhere. Let's go to the midpoint. So this is going to be 0. It's a number line. This is your plus or minus L here. Okay, so we know with L value, we have the L value. Again, for a D is 2. So we're going to go plus or minus 2. So this is 0 plus, oops, let's change that a little bit. So we have 0 plus 1 plus 2. Here, number line, minus 1, minus 2. So here, same thing, 0 plus 1 plus 2. This is minus 1, minus 2. And so in here, we have a plus 1/2 spin in the plus 2 ML value or location. And for cobalt, our last electron in is spin down and it's -1 ml location. All right, so there you have it. That's how we look at spin values with regard to the electronic configuration.